So we're gonna start the fundamental theorem of calculus, and like it sounds, it's kind of a big deal. We have 4 days to go over this stuff, and so I'm really gonna try to break it down into sections that make sense. And this starts on page 378. We're only gonna do just the beginning on this video, and then we'll talk about the rest of it on Monday or next time we see each other, or maybe I'll make another video, etc. But the lead in, and this is definitely something that you guys are going to want to read a couple times, and so um, just keep that in mind, that maybe just one time through is just not going to be enough. But we were talking about in the last section, um, the connection with Riemann sums and the definite integral. And we already kind of said this, but Riemann sums aren't necessarily great, as in they give us an approximation. And then when we take the limit as the change goes to 0, then we get an exact value. Now, that's kind of clunky to do, right? I mean, that was, you guys even mentioned it. Like, that's a lot of writing things out and evaluating this limit. And we need that connection. And, I compared it to when we first learned about a derivative. We had to take the limit of that difference quotient as our h value approached 0. And that was the definition of a derivative. But then we started learning our derivative techniques. And so, the last thing we talked about before in that last section was very similar. We said the definition of a definite integral is the limit as the change goes to 0 of that summation statement. And so what we're working toward is some integration techniques, but we're in the middle of it right now. And so we have to find this connection between the limit and then just going straight to our integration techniques. And that's what this first part is about. And really, that's what this whole section, the fundamental theorem of calculus, is about, is making this connection. Now, you should understand that mostly what we're talking about here is area under a curve, remembering that anything above the x-axis adds positive areas, anything below the x-axis starts adding negative areas. And then you just add those together and you get the total net area. So we're going to talk a little bit about area function right now. And I didn't bother taking a picture of the first part. They just give you the introduction paragraph, but then they start talking about area functions. And I'm going to, the picture I have here on the screen is really the big deal, right? This here. And it's going to be referring to this. So I'm going to say some things, and it's important to keep things straight. And the first thing you want to understand here is that we are creating this area function denoted by a of x. And it is just like any other function that you've dealt with. You're going to plug in values. Now, what are those values? And so then we're going to look at this picture for a second and kind of looking at both of these things at the same time. Remember kind of the notation over here is that we're going from our left endpoint to our right endpoint. But notice how they write a and then x. They're not using b right now, because the idea is that we want to find the area under a curve starting at a, but then going down as far as we want. So we're not limiting it to any specific number. We're just saying we're going to keep going. So like if you look over here, like if this was our curve that we wanted to find the area under, then maybe we want to stop here, and then instead of x, we would plug in whatever value that is. And we could keep going, and then eventually we get, the picture just runs out and says this keeps going. And so we could put in whatever we want. So the idea will be the same in that we would just go from left endpoint to right endpoint. That would represent the area under the curve over that interval. We just don't want to limit it, and we can just say it's going on and on forever. So this area function that we are going to create the x value that you would plug into it is representing just the right endpoint of how far you're going to go down. We have to have a starting spot, A, and then, how far do you want to go down? It doesn't matter. You're going to just put that in there. But really, you're putting it in here first, right? So in this case, we would just say, well, maybe our value, like if we pretend A is like 1, you could say, okay, the area, A of X, I want to plug in 2 here. And so what you would be saying is, my right endpoint would be 2, if we pretend it's right there. And our area function would generate a value that would represent the area from A to B under that curve. Or maybe we'd go, 2 was our example. Or maybe we wanted to go to 3. And so when we plug 3 into this function that we're going to create, this is how we're going to create it. But when we plug the value in, we would still start at A and then go maybe a little bit further. And the value that would come out of this function will represent the area of that little bit more. Okay, so it is important to keep a couple things straight when we're talking about that. And the first thing, and I'm going to re-say it basically, is that this is going to be a function that we are allowed to plug in a number. Our output, and this number is going to generate basically, if you're thinking of Riemann sums, it's going to generate our width, the number that we plug in. The number that comes out, our output, will be the exact area under the curve over that interval that we chose. Now they get a little technical as they go through here, and they say, so they talk about, and again, make sure I would definitely read this stuff a couple times, and hopefully my explanation gives you a little bit to go on. But a lot of what they're saying here is saying, okay, so that's what x is, what I just described. That's what our x value is. Notice that we have a different variable in here because we're generating an area function here. The x value can't be the same here. It doesn't match up that way. It's not like what you're plugging into this. So we're going to make what they call a dummy variable, and it can be anything. They're just using t. And then we're going to treat this f of t a little bit different than f, it is not f of x. The x is being applied to only the area function. So to keep going off of that, I think this is a really good picture to start with. It's kind of describing what I said a second ago. So we have created this area function, okay? At one point, these pictures look basically like this. It was just a of x, just some function that gave us the area. Okay, and so now they're saying, well, if we pick a value b and plug it into our area function, what we're really doing is say, find the definite integral from a to b. And so then they limit that here. And so this area would be here. Or we can move it down a little bit and say, let's plug in c. And so instead of getting this little area when we plugged in b, the output would be this area. Now we're going to plug in c, and then we would get this whole area here. And we could keep going on this idea, right? If we move down a little bit further, and we plug in d into this function that we're creating, then that would say, give me the area all the way, the net area all the way from A to C, or I'm sorry, all the way to A to D. And so then what this statement is saying is like, okay, so you found this area, and now you're going to add this area to that. And then of course, this would be a negative thing. And again, it's very important to understand that what we're really creating is a function whose output will be an area. And so and this is representing just the graph of what the area function would do. And so then why is it in this shape, right? Why is it going up and then coming down like that? Well, let's look at the example that they're giving. And so as we're going from A all the way to C, when we go from A all the way to C, we're getting a positive area. It keeps increasing. It was 0 here, right? That's at one part of that theorem. If we haven't moved yet, the area just at this left endpoint would be 0. We haven't accumulated any of it yet. But as we move down, we keep increasing our area. Now, why is it slowing down? Well, this area that we're adding toward as it comes closer and closer to the x-axis, is getting smaller and smaller contributions. It's still adding area, but just at a slower rate, right? Because this is like shorter and shorter. And then once we get to all the way to C, and if we wanted to keep going, what this picture is showing is that we would start adding negative area. And so then that's why our overall area will start decreasing, and it'll keep decreasing until we get far enough down this t-axis so that the area below the x-axis is equal to the area above the x-axis, and we would be down here where we plug in whatever that endpoint would be, and it would cancel each other out. And so then our area function would say, oh, there's 0 area here because it's adding the negatives and the positives. Okay, so that's kind of the idea of what's going on here. And I know the important part is to understand that the value we plug into this function that we're going to come up with is going to give us the overall area underneath the curve, whether it's positive or negative, how much of it is, of that function from our starting point to whatever number that we pick. And that's the important part to understand. So now we have just this definition, and this is really the thing that you guys are going to do today. Okay, and so here's the definition of an area function. Let f be continuous function. The area function for f with left point endpoint a, and a is going to be a number. It's not going to be a variable. It's always a number. Is going to be this thing that we looked at on the previous page. A of x equals the definite integral evaluated from a to wherever you want of this function. Okay, so where x has to be bigger than a. The area function gives the net area, right? The contribution of the positive area and the negative area, bounded by the graph of f and the t-axis on this interval. So instead of going through the example, I'm just going to go over number 12, and you can use the example as like kind of a refresher of what's going on since they walked through it. It says the graph of f is shown in the figure. Let a of x, our first area function, have a left endpoint of 0. That's kind of what they're saying. And then we'll go forward from there. And then we're going to have another area function we're going to call f of x, right, big F of x, where the endpoint, left endpoint is 2 instead of 0. And so both of these are going to be area functions, and they're both going to be area functions about the same function. We just have 2 different starting spots. Evaluate the following area functions. Okay, so we're just going to do each of these, and then hopefully this will make sense. So part A is saying a of 2. Okay, so what we have to take a look at is, okay, A is saying start here at 0. So a of 2 goes all the way here with an area of 8. So then, right, a of 2 equals 8. Okay, so then B is f of 5. So, we're finding an area function, we're evaluating it at 5, but now we're starting at 2. So now we're starting at 2, going to 5. The area is 5. Of course, it's below the x-axis. So f of 5 is equal to negative 5. Okay, and so we're going to keep going through that. So a of 0 is part C. Right, make sure we start at the right place. Right, the left endpoint of A is already 0. And so since we're evaluating at 0, we're not accumulating any of the area, so then it's going to be 0. So now we're going to f of 8. Right, f starts at 2, going all the way to 8. So that's a negative 5 and a negative 11. Then together it would be a negative 16. Okay, and then we're going to look at a of 8. Okay, remembering that a starts at 0. So we have this negative 16, but then we have a positive 8. So the total is going to be negative 8. Oops. Part F would be a of 5. So again, we're starting at 0, going all the way to 5. That's a positive 8 and a negative 5. So then a positive 3. And then finally, G is f of 2. Okay, so f of 2, right, that's where we start, right? Our left endpoint is at 2. So again, since we're not accumulating anything, the area would be 0. Okay, and so that's the basic idea of what our area function is going to do. Now, there's one other thing that they talk about in the example, and that's something that's going to be important when we get to the actual theorem of the fundamental theorem. You notice that they kept giving us the similar ones. So, for instance, we have a of 2 and then f of 2. And we have a of 5 and f of 5. And we have a of 0, but that wouldn't make sense to do with f. Okay, but then we have f of 8 and a of 8. And so then there's this interesting thing that happens when we look at the difference between these two area functions at the same endpoint. And so let's look at, we'll just do the 2 first. So they're not asking you this right here, but then this is kind of like what part of the idea is. I'm going to keep that so we can see it. So if we take a of 8, or I'm sorry, a of 2, we're going to start with, and subtract f of 2, right, we would get 8 minus, where'd it go, 0 for 8. And then if we do a of 5 minus f of 5, we would get, where's a of 5? 3 minus f of 5 was a negative 5, we would get 8. And if we do a of 8 minus f of 8, we get negative 8 minus a negative 16, and again for 8. Okay, and so this is going to be an important part of the fundamental theorem. And so basically what they're saying is, if you evaluate two different area functions for the same function at the same endpoint, they differ by a constant value. They're all 8 here. So 13 through 21 are essentially all the same. There's a little bit different, like number 17, I think maybe is a little bit different. So yeah, 17 is a little bit different. But I think if I'm just going to do number 19 here, or I'm sorry, I'm going to do number 20 here. And I think that you'll be able to apply the idea as you go forward, but you just got to make sure you ask, and if it doesn't make sense. But so I'm going to do number 20, and it says consider the following functions f and real numbers a, and then find and graph the area function a of x, and so that's what we're going to do first. So again, I'm doing number 20, and they give us this function. Okay, and so then again, just so that we're all, we're creating this, and how we're doing it, and we're putting a 0 there because that's a. And so then I'll, substitute in a little bit more. So before I go on, let's make up some numbers to see what we're trying to accomplish here. So, they give us this, and that's basically what our function's going to look like, right? We have a positive slope, and it's starting above the x-axis, so that's a pretty good representation. We're starting at 0, so pretend that this line is the y-axis. And so let's say, like, if we're starting at 0, let's go to 3. Let's pretend that we're just finding the area, right? So for this, like, kind of think through example, and this is kind of how they talk about this idea in the example, so hopefully this will make sense. Hopefully the example makes sense if you take a look at it. So let's say we're doing that. Now, what shape does this form? Well, this forms a trapezoid. So, I said this earlier, but you do need to know the area formula for a trapezoid. So what is the area of a trapezoid? Well, that's 1/2. So it's basically, basically this is saying average out the bases and multiply it by the height. Okay, so this trapezoid is off on its side, so you got to keep that straight. So the height, let's talk about the height first. The height would be found by taking your endpoints and subtracting them. So, right, our height ends up being 3. But we ended up subtracting them to find the difference between the two. Okay, and so then how do we get the bases? So the 1/2, we're going to leave that alone. So how do we get the bases? Well, for our problem, that is f of 0 plus f of 3. Okay, so then what we would be saying is that our area, if that was the case, would be 1/2. We're plugging in 0 here. So 1/2 of 5, that's f of 0, plus f of 3, right? That'd be 611 times 3. So then the area of the trapezoid for our example would end up being 8 times 3 for 24. Okay, so that's the idea, and what I'm going to point out is, right, to find our height, we had to subtract the endpoints. To find our bases, we had to evaluate our function. Where to go? Right, we had to evaluate our function at the endpoints. That gave us our bases. So we evaluated at 0 and we evaluated at 3, added those numbers together, divided it in half because that's the formula for a trapezoid, and multiplied by 3. Okay, but what we're doing is we're not doing it for every point. We want something, a of x, so that we could just plug in the second endpoint and get that area right away. We don't want to have to go through all of this every single time. We just want something that we plug in. So then it's going to be very similar to what we wrote here. Okay, so we're just doing our endpoints being 0 and x now. That's the only difference. So let's see what happens, and we'll keep that on there so we can see. So then, since this is making a trapezoid, and this is only because it's a trapezoid, this is very specific, we're going to say, well, this area function is actually 1/2 times the bases. Well, what are the bases? They're f of 0, right, our first endpoint, plus we don't have a second endpoint, we're going to just call it f of x, right? That evaluated gives us the heights. And then we want to multiply it by the height in terms of the trapezoid, which is where we take our right endpoint and subtract our left endpoint from it. So now we're just going to evaluate and simplify. 1/2, we already found f of 0 before, so we're going to still use that as 5. But now it's just plus this function. Well, this function is, the function that we start with is 2t plus 5. We're evaluating it now at our right endpoint, x. So now it becomes 2x plus 5. And now that's times, since we're starting at 0 and going to x, the height of our trapezoid will be x. And so now all we have to do is simplify it down. So we have 1/2 times 2x plus 10 times x. So then it's x times x plus 5 for x squared plus 5x. And so this, we just created the area function here. And now we have an example over here that better work, or otherwise something else went wrong. So what we're saying on our original example was like, well, what's the area if the right endpoint were 3? Well, let's just check just to make sure. So a of 3 would be 3 times 3 plus 5. So sure enough, it's 24. So this is our area function, and that's the idea. Now, of course, this is a linear function, so it's very easy because you're just making trapezoids. You do 13 and 15, it's even easier because it's just a constant, so you're doing the area of squares, but you do it the same way, right? You find your heights by plugging in your endpoints into the function, and then you multiply, well, I guess you only need one height since it's a rectangle, and then you would multiply it by the distance from your two endpoints. Okay, so it's all the same, just easier. Now, that was part A. We just did part A, and then part B says verify that the derivative of that is actually f of x. So if we're finding the derivative, right, we get 2x plus 5, which is the same with just a different variable of our original function. Aha! This is where the connection comes in, okay? Now, what the book is going to say is like, they're going to go and say, well, it looks like, and this is kind of going into the next day, what they're going to say is, well, what it looks like is that if you get a function and you want to find the area function of it, basically you're just doing an antiderivative. And that's what this connection looks like. And then they say, well, okay, is that true for all functions, or is it just true for linear ones? And that's where we go from here. So your assignment for today, or for this section, will just be 11 through 21 odd. You get this area idea down, then you're going to be you're in good shape. Okay, so make sure you ask some questions if you need to. And the other thing is if you're not understanding, I think you'll do fine on 13 and 15, but if you're not understanding number 17, I think it's kind of everything combined, but kind of just look at the notation. I think you'll figure it out, but send me an email or whatever, or ask about 17 in some way.